All right, so this is a solution of a non-homogeneous problem. So there are several ways to find solutions to non-homogeneous problems, but I'm saying find a particular solution to the non-homogeneous problem. And this, you might remember this from your differential equations class. If you have a non-homogeneous problem, the general solution, this is from ordinary differential equations. If you have a non-homogeneous problem, the general solution is going to be equal to the general solution to the homogeneous problem plus a particular solution to the non-homogeneous problem. And that's kind of what we want to find here. We want to find that particular solution to the non-homogeneous problem. So it's kind of like what we will, well, you'll see as we go along, but the idea is that the general solution, meaning like the general part is the f of x. So that's sort of the thing that plays the role of the initial condition. So this will make a little more sense, I hope, as we move along. So what we're going to do is we're going to start by finding, just taking the Fourier transform of both sides. Okay, first take the Okay, so when we do that, when we take the Fourier transform, we're going to get this on the left-hand side. On the right-hand side is going to be minus omega squared hat u of omega t. And then, well, it's just going to be the Fourier transform of q. We don't know what the Fourier transform of q is. It's just whatever it is. So that's why I think I say here your answer will be in terms of the Fourier transform of q. Okay, so let's just see what we got here. Okay, so now so what we're going to get then is, let's rewrite this equation like this, not dollar signs. Okay, so this now is a first order differential equation, but it's not homogeneous. So it's going to be plus omega squared u. Now there's a couple of different ways to approach this, to solve for u hat now. There's a couple of different ways we can approach this to solve for u hat. I'm going to let you think for a moment. There's one kind of standard method that we solve a first order linear non-homogeneous problem. Think about what that is for a minute. Pause the video because I'm going to go right into it. Okay, hopefully you paused and thought about it, but it is integrating factors. So we're going to use integrating factors. So we will solve this using integrating factors, and since there isn't enough letters already and symbols, we're going to introduce a new one. So it's the t variable that we care about. So mu of t is going to be equal to e to the antiderivative of whatever is there, but it's the antiderivative with respect to t. So it's going to be e to the it's the antiderivative of omega squared with respect to t. With respect to t, omega squared is a constant. So this is e to the omega squared t. Okay, so now, see, so you really have to remember your stuff from differential equations, okay, to be able to do this. So now on the left-hand side, remember the whole point of the integrating factor is when we multiply the left-hand side. Meaning that side. Actually, let me compile this so I can show you what we're looking at. When we multiply the left-hand side by the integrating factor, it becomes the unknown function, or the derivative of the unknown function times the integrating factor. That's the whole reason we multiply by the integrating factor. And actually, now that I realize it, we don't even need to have mu here. Okay. When I multiply the left-hand side of the integrating factor, it becomes the unknown function, which is this, times e to the integrating factor, which is omega squared t prime. That whole thing. By the product rule, if you do this, you're going to get the left-hand side times the integrating factor, and then on the right-hand side is e to the omega squared t. Again, that's the integrating factor times this. So let's see what we have here. Okay. All right, so now what we're going to do, instead of writing the prime here, I actually want to write this. I think I want to write it like this, d dt. So let's see what we have here. Okay, so now what we're going to do is we want to differentiate. We want to anti-differentiate, but we want to use the fundamental theorem of calculus. So typically when we have something like this in a differential equations class, we just anti-differentiate, and on the right-hand side we have a plus c. I want to actually use the fundamental theorem of calculus to integrate both sides from one point to another. So what we're going to get by the fundamental theorem of calculus, if we integrate both sides from 0 to t, okay, so when I integrate the left-hand side from 0 to t, I'm going to get this minus this, but evaluated at 0, at t is equal to 0. Okay, that's the fundamental theorem of calculus. That's just the fundamental theorem of calculus. When you integrate this from 0 to t, it's just going to be, when you integrate the derivative from 0 to t, it's just going to be this evaluated at t minus that evaluated at 0. Okay, and then on the right-hand side, this is going to be the integral. Okay, so now t is my variable, so I'm going to use a dummy variable, so it's going to be s equals 0 to t, and we're going to integrate e to the power of omega squared s times hat q of omega s, s ds. Okay, let me see what this looks like. Okay, that's good. It kind of looks like that's a subscript, so I think I'm going to write this like this. Looked like that was a subscript, so I'm going to write it like that. Just switch the order here. Okay, now we can treat this. We can treat this as this is our constant. Actually, let me not explain it that way. And so we have the following. This, well, this is going to be equal to. So let me remind you. U hat is just f hat. So this is f hat. Sorry, u hat is not f hat. U hat of omega 0 is at f hat. So this is f hat of omega. Then I need to divide by e to the minus omega squared t, and then it's going to be plus e to the minus omega squared t times this integral. And I'm going to have to stop this for a moment and come back. It won't matter to you probably, because you'll just continue the video right along, and hopefully the video won't get messed up. You'll probably notice this time here, skip ahead about 30 minutes or 40 minutes or an hour or something like that. Okay, I think I'm back. I think I'm recording the right thing. All right, so we are finding the inverse Fourier transform here. But notice we're asking, so this is where the sort of the particular solution comes in. So the inverse Fourier transform of that is just a solution to the homogeneous problem. Okay, so since we need just a particular solution, this is the inverse Laplace transform, Fourier transform of this function here. Whoops, what happened? Why did that? Maybe I just typed too fast. Probably not. There's probably a mistake I'm not seeing. Okay, so the inverse Fourier transform of that. And think about what I'm saying here. We only care about the particular solution. This solution right here is a solution to the diffusion equation. Okay, and so this right here is going to be a particular solution to this non-homogeneous problem here, right? But it doesn't give us, it's not going to satisfy this property here. In fact, when t is equal to 0, it should equal 0. Okay, because the overall solution is going to be the inverse Fourier transform of that, which is just the solution to the diffusion equation with this initial data, plus the inverse Fourier transform of this, which will be the solution to the full non-homogeneous problem. Okay, but it's not going to satisfy this initial condition. And when I say a solution to the full non-homogeneous problem, really what I mean is something like this. I'm not going to write this. I mean, I'm not going to keep this. It's a solution. If you look at pt minus pxxu equals q. So if you look at this, this thing here is a solution to this problem. Meaning, if you take it and plug in, meaning if you take it and plug it into here, you're going to get q. Okay, so the overall solution is going to be a sum of these two guys right here. When you take this and plug it into the PDE, the inverse Fourier transform, the solution corresponding to this, when you plug it into the left-hand side, is going to be equal to 0. Sorry, let me compile this really quickly. When you take this, or the inverse Fourier transform of this, and plug it into the left-hand side, the part corresponding to this, that's just a solution to the diffusion equation. So that minus that, when applied to the inverse Fourier transform of that, just that part there, is going to be equal to 0. And then when you do the t derivative of this, or the t derivative of the inverse Fourier transform of this, minus the double x derivative of the Fourier transform of this, is going to be equal to q. And furthermore, the inverse Fourier transform of this, which is just written again here, the inverse Fourier transform of that, when t is equal to 0, notice we're just going to be integrating from 0 to 0, and we're going to get 0. Okay, which is what it should be, because if you look at the inverse Fourier transform of that and evaluate it when t equals 0, you get f of x. Okay, so sorry, that was a little rambly there, but that's what we want. And this is, there's nothing more that we can do here. I'm going to call it u sub p of omega t. Sorry, that's going to be x. Let me just... So this is the Fourier transform of the particular solution, basically. Not basically, that's exactly what it is. This is the Fourier transform of the particular solution. Okay, I think I need to do wide hat to put this properly. There we go. Okay, so u p of xt, all we're going to do is just the formula for the inverse Fourier transform, but I need to do an equal sign there, don't I? Okay, so it's just going to be the inverse Fourier transform of this whole thing here. So it's going to be the integral minus omega equals minus infinity to positive infinity. And if you're wondering, I just like to do, I like to put the variables here explicitly just because there's so many variables going on. And then it's going to be d omega. Let me see how this looks. Okay, it's that. And what I'm going to do next is I'm just going to combine this into one integral. Or not, sorry, not one integral. That didn't make sense. I'm going to, you'll see what I mean. So I'm going to have this. I'm going to take this guy, which is in between the integral signs, and put it right here. Oh, sorry. I've made a mistake here. So the dw, I need to have e to the I omega x I forgot that. So it's going to be like this here. I'm going to change that though. Except I don't want that D. Okay. What has happened? Undefined control sequence. What have I done? Oh, because I don't have a space here. All right. Okay, so let me put this in parentheses here. So the left parenthesis, left open, right closed gives me big parentheses. So we get something like this. So this is just the function of omega. Okay, and now we're doing the inverse Fourier transform. And we get this. Okay. And now I'm just going to start this part over again. What a mess. Okay, so now I'm going to get rid of this here. I'm going to get rid of that there. I'm going to put this inside the integral. Let's say here. I'm going to put this inside the integral. Let's say I'm going to put it here. Let's see how that's going to look. Okay, notice we can just combine that all into one exponential. So we'll have these integrals like this. So you know, stopping here or something is fine. I'm just going to go a few steps more to see how I can make it look. So we're going to have this like that. And then now we're going to have e to the power of minus omega squared t plus s omega squared plus I omega x like this ds d omega. Did I do this right? Omega squared t, omega squared s. Oh, I have it that way because it looked like there was a superscript before. Okay, so down here, I can write this as omega squared times s minus t. I think that'll look a little easier. Okay, and then there's a number of different things we might be able to do here as well, like you know, complete the square, whatever, in the numerator, or not the numerator, but the exponent. But for now, I'm going to leave it like that. Actually, one last thing I'm going to do. I'm going to interchange the order of the integrals here. Okay, so I'm going to put this integral on the outside, which means this differential needs to go on the outside. Space there, and I think that's going to be it, so I'm going to put a period. Okay, yes, so this looks good, looks like what I want to have, and okay, that's going to be it for this problem.